So welcome all of you for today's session. So week 9 live session for advanced research trends in smart grid technologies. I'm Gagan Meena and I'm currently doing PhD in Electrical Engineering Department at IIT Bombay. So this will be the agenda for today's live session. First of all, we will briefly go through overview of week 9 and we'll spend some time on some important topics, and then we will discuss some questions regarding the week 9 material. Simultaneously, we will also discuss some relevant topics, and then finally we can have your doubts. In between also, if you have any doubt, you can ask. So is it fine? So just to remind you that deadline for assignment 10 and 11 is April 5th and April 12th, so try to submit within the deadline. And you can also find the recorded live sessions on this link, which is also available on the portal. So let us go through the overview of week 9. So in week 9, starting from week 9 and the next subsequent weeks also, we will go through some demonstrations of concepts which have been discussed in previous weeks, while also explaining some important concepts. So in this 9 week, we started with the demonstration of solar power generation and the wind power generation, and then the demonstration of the cell balancing, which is one of the functions of battery management system. So we saw the demonstration of active and passive cell balancing techniques. Then we saw some concepts regarding the EV charging system, different types of chargers, different modes of charging, and other important things. Finally, we discussed this hierarchical control techniques. Some of this part of this lecture was already discussed in previous class, and we will go through only those which are the new additions. So let us start with the demonstration of the solar power generation first of all. So how many of you have already some idea about OPLRT or RTDS? Have you heard about these terms? Any of you? No. Okay, no problem. So as you would have also seen in the lectures, so in solar we are using OPLRT, and even in the cell balancing, which is the third lecture, battery management system, there also for the active cell balancing technique OPLRT was used. So we used it for solar and cell balancing. Then in wind also, we'll see in subsequent slide, we use this FPGA based controller for controlling the DFIG. So this is called field programmable gate array. So it is a processor. OPLRT is also a processor. And then there is one RTDS also, which is called as real-time digital simulator. So these are very, especially these OpenRT and RTDS, these are very fast processors, very high speed processor which operate with very high frequency, even up to gigahertz, several gigahertz. They have several very fast RISC based, FPGA based, DSP based, very fast processors, multi-core processors, which can be used to do several computations within microseconds. So their time step is in order of microseconds. It may be even less than that. So they can do computations within this range. So we can say it is almost like real time. So what is the need of these things? So suppose we want to simulate just as here we are doing. So in cell balancing, what we are doing, we are implementing one algorithm. If we see the actual ICs, they are the real hardwares which implement the same algorithm. But we don't have those ICs, so what we do, we use these processors and we dump our code or our simulation. If they have, like this OpenRT has interface with MATLAB Simulink, so we can develop our algorithm or the control module, control blocks inside the Simulink. Then Simulink has an interface with this OpenRT. So whatever we have designed inside Simulink, that will run on this OpenRT hardware, which is a high-speed processor. So now this OpenRT, our control system is inside this OpenRT, and this will act like a hardware for us. We can say it will act like an IC for us. So we can give it some input and get some output. So here in case of solar, we are using this FPGA based processor. FPGA we are using in wind. Here in for solar we are using this OpenRT. So we are developing our control logic inside this OpenRT. So OpenRT will receive currents and voltages, and it will give the firing pulses for this IGBT stack. So OpenRT, all these processors have some input terminals and output terminals for both analog and digital type. So they have analog input pins, digital input pins, analog output pins, and digital output pins. So they can take the input, analog input, then inside they will be having ADCs which will convert the analog into digital signals. Then they will perform the entire computation in digital domain, and then they will give some output. So depending upon our requirement, we can get digital output or analog output. Since we want to give this output to the gate circuit, so we can take digital output also for firing pulses. So any doubt up to this point? Is it clear why do we need these kind of processors? Similarly, this grid emulator also. This is also emulating the grid, actual grid. Although this is not the actual grid, but it is acting like a grid. So we are, whatever the solar plant is generating, we feed it to this emulator. So this is our source here, which is a programmable DC source which will emulate the PV characteristics. So we have these two characteristics here, IV and PV characteristics. So these two we can emulate using this programmable DC source. Because it is programmable, so we can get any output based upon our requirement. We can program it. So this is our source here. Our control system is inside the OpenLRT. This is for monitoring. This is, you can see, Simulink block where we are developing our control logic. Since here we are using only single stage conversion. This is grid emulator, and then since the OpenLRT requires current and voltage signals, and then it will give the output to firing pulses to this IGBT stack. So this is the IGBT stack. So output of OpenLRT will go here. To this gate driver circuit. So is it clear up to now?
Yes, clear. Go ahead, please. Go ahead.
Okay. So we have, so for solar we can have single stage or two stage conversion, right? One is we directly connect the output to our DC bus, and then we have a single DC to AC stage, so which will perform both the function of MPPT as well as regulating this voltage. On the other hand, you can have a two stage also. First stage is DC-DC, then DC-AC. So which configuration will be having more losses?
Second is there because two times.
Yes, correct. So second will be having more losses because of the more conversion stages. So in these two stages, which stage will be doing the MPPT control?
Please repeat the question again.
So we have two stages, right? One DC-DC and one is DC-AC.
Yeah.
We have to perform two functions. One is to extract the maximum power from the solar PV, and then we want to regulate this voltage also, because so it is, you can consider it is in grid feeding mode. So it will supply P and Q, right? So which of these converter will perform the function of MPPT?
MPPT first one, DC to DC.
Correct. So this will ensure that maximum power is extracted from the solar PV. In single stage, this inverter itself does this function, and also generating the required P and Q. So we have in the yes.
Bomb 2 is says is having loss, but it is more beneficial. No?
How?
MPPT,
Yes.
then it will draw maximum power. No? Then some losses will be there that will compensate it.
Even this single stage is also doing both the function. It is also extracting maximum power. The function, whatever performance this is giving, is output.
Yeah.
Even this is extracting maximum power and also feeding P and Q. This is also extracting maximum power and also feeding P and Q. So both are doing same thing, but this is having more losses, this is having less losses. So we prefer single stage.
Yeah, definitely. Then why it is? Some benefit it may have.
Initially we started with this 2 stage.
Okay.
Then later we developed this single stage.
Okay.
So earlier we used to have this DC-DC which used to implement the MPPT. So it would be a buck boost converter.
Okay.
Then we were having one more inverter, DC-AC. But now the same inverter is doing both the functions. It is extracting. Yes.
Maybe due to compact design and better components.
That is true.
Maybe.
Because of advancement in this power electronic technologies, so the design is getting compact. So that is one reason, and also because of this new type of devices that we have.
Yeah.
So these are the different reasons.
Okay. Right. Please go ahead.
So, do you have any doubt in what was discussed in this demonstration of solar? Anyone?
No. Not clear. Go ahead.
How was any? If you have any doubt, you can ask. Otherwise, we'll move to the next topics. So one thing was that did you understand that? So here we are using one IGBT stack, right? Which has 4 modules, and each module has 2 devices, 2 IGBT devices, which are in series. So total there are 4 lakhs. But for this single stage conversion, where we are considering only balanced system, so we require only 3 lakh. So what are we doing with the remaining 1 lakh? Can anyone of you tell? So these 3 lakhs we are using for the DC-AC conversion stage inverter operation. What are we doing with this 1 lakh? Any of you? So we have this, right? So we have 4 such legs. Then we have snubber also, that I'm not drawing. And then we have so this is a boost converter. Yes, we are only using 3, but 1 we can also use if you want to introduce this DC-DC stage. So we can use it to make a boost converter. So if you want to make a boost converter using this, how are we going to do that? Well, this is M1, this is M2, this is T1, this is T2. So which 2 switches should I choose? So I can say this is L, right? This is A. So this is L, this is point A. Now can anyone of you tell how to make this using this? And we have one capacitor here. This is for each. This is a snubber capacitor. So let us for time being remove these. We already have this. We want to convert this into a boost converter. So simple thing what we can do, we can use this. If you use this, it becomes same, right? These two are same. We have a switch here, diode in series, then a capacitor, and then we can place our inverter here. Right. So is this okay? Is this fine?
Yes, yes.
Okay, so let us move ahead then. So this is the single stage solar inverter control. So here we are having how many control blocks? One is this MPPT control, then DC link voltage control, then AC current control, and then one is this PLL. So this block is used to synchronize our theta with the theta, because we take voltage from the grid reference. Suppose it has this is a grid theta. At PCC we have a voltage, grid voltage, and the angle is theta G, and output of PLL is theta. So this we want to synchronize. If we do that, we get some benefits in the DQ frame. So here we have 1, 2, 3, 4 control blocks. Then in 2 stage, if we do, then since the first stage is the MPPT, tracking which is taken care by the DC-DC converter. So here we have again this similar, only PLL is not here. PLL is not required here, it is required for the inverter operation. So here for the second stage where we have DC to AC conversion, we have this PLL here. Now MPPT part is already done, so remaining blocks are there. 1, 2, 3 and 4. Again 4 blocks. So let us move to the second one, demonstration of wind power generation. So this we already know, we have already discussed this. This is the main part, demonstration. So here what the main components are this, one is the DFIG, then its control, which we also call it wind emulator, and then the back-to-back converters. So this DFIG is coupled with the DC motor. So the DC motor acts as the prime mover of the DFIG, because we have what we have here, we have this wind turbine. So here the DC motor, in our demonstration the DC motor will act as a wind turbine. But how are we going to produce the wind characteristics, different types of wind? That we are going to do by controlling, by using a control block. So we are going to control this DC motor so that it behaves as if the actual wind is behaving, actual wind turbine is behaving. So that control we are doing inside a processor. Here we are using a FPGA based processor. So this is that processor. It's way back. This is the FPGA based processor. Entire control we are implementing inside this processor. So this processor will finally generate the firing pulses for this back-to-back converter. Is it okay? So these are the two control. So we are saying these are the 6 pulses which are generated by the rotor side converter. So all these 2 blocks are implemented inside that processor. So we can use different types of processing. Here FPGA has been used. So this is the part for MPPT. Here you are using perturb and observe technique. There are different types of technique. Even for solar, P and O can be used. Then there incremental conductance technique is also there. Method. P and O is another method. So there are other different types of methods available for this MPPT tracking. So using this method we are generating this reference feed and then doing the entire control. So is there any doubt in this wind power generation demonstration? I just quickly going through these topics so that we can, when we are discussing questions, we can easily do them. We can remember certain things.
Please explain some in detail. Is control logic?
This control logic.
Yes, little bit.
So what we are doing now here, so we have these so this is our DA file, so then it is going to the connecting it to the grid. So this is stator power here, this is rotor. So this is a grid side converter and this is the rotor side converter. So what we are trying to do is, when the wind speed changes, so we want to change our power also, power input, power which we are feeding to the grid also. Because wind is changing, so power will also change. So depending upon the wind speed, we have to extract maximum power from that wind. So this is a variable speed drive. Although wind may change from 5, 8, 12, but whatever wind we have, from that wind we want to extract the maximum power by changing the pitch angle. So for that we use this block is used for that, for generating the MPPT reference. And as per the grid norms, we have to feed a fixed frequency power into the grid. We have 50 Hz, so we have to inject 50 Hz only. So suppose the wind speed is less than, the rotor speed is less than the synchronous speed. So then what will happen? The rotor is, slip is omega s minus omega r by omega s. So in this case the slip is positive, but the rotor speed is less, so the rotor will take power from it has to take power from the grid in order to ensure that stator supplies a fixed frequency power into the grid. In case of overspeed, when the rotor speed is more than the synchronous speed, the reverse will happen. The rotor will feed power into the grid. So by ensuring this bidirectional power flow, we are able to maintain this frequency. So this is the reference frequency, this is the standard or the estimated frequency. Then we are using the PI controller. So the error will go to the PI controller and it will track the signal. It will generate a current reference based upon this error. And the actual current which is there from this rotor side converter, we take error from that, again we send it to the PI controller. So all this we are doing in the DQ frame. There are certain what is the need for DQ frame is because we want to use simple control. PI is the simplest control, and PI controllers will work on linear signals. So constant signals, you can say. Here these DQ signals are constant signals. They can vary in transient, but in steady state they are constant. But if we take the actual ABC signal, those ABC signals are sinusoidal signals. We cannot track these sinusoidal signals using a PI controller. For that, we have to use a PR controller, proportional resonant controllers. if you want to track these sinusoidal signals. But using these PR, the design of controller becomes very cumbersome and complex, and the order of system becomes very high. Therefore, we mostly people use these simple PI controllers by using this DQ frame transformation. So here this current, this ID current is generating this VD star reference. Similarly, the IQ we are getting from here MPPT. By comparing this generated reference using this MPPT reference, we are comparing it with the actual Q current. How do we get this ID and IQ current? We take the actual rotor current which are in the ABC domain. Actual rotor current, physical currents are all in ABC. They are sinusoidal signals. We are using here these 3-phase induction motors. So they will give ABC 3-phase current which are sinusoidal. But inside the controller everything is in DQ frame. So while measuring this rotor current, we will get this ABC current. We have to convert it into DQ current. So here we will get the ID RSC and IQ RSC. So these are the two current, this ID RSC and IQ RSC, and we are comparing it with the reference we are generating using different. So for IQ we are using this MPPT to generate the reference, while for ID we are using this frequency error. So then again we are converting the voltage references into the ABC frame so that we can generate the PWM signal for the rotor side converter. So here we are, for PWM we are using this sinusoidal pulse width modulation. So for that we need these sinusoidal signals. Right? So is there any doubt? Is it fine for rotor side converter?
Yes. Now clear.
So similarly on grid side also, the grid side, the main function of the grid side converter is to maintain this DC link voltage. So this RSC and GSC, they have a DC link capacitor in between, so we want to maintain that voltage. So that reference DC link voltage, we have set we have set this voltage, and this is the actual voltage. We are comparing these two, and then we feed it to a PI controller, which gives us the voltage reference, the current reference, and then finally the voltage reference. Similarly for the reactive current, also for IQ, this IQ reference star also, we can get based upon the reactive power requirement that we want to feed into the grid. Because if the converter, the DG is in PQ, operating in PQ mode, so we know how much P and Q we want to inject. So based upon this Q reference and P reference, we can based upon this Q reference we can generate this IQ reference. This is also generated using the equations. So we can determine these values because depending upon the Q we want to inject into the grid. Then after generating this Q star, we compare it with the actual current and pass it through the PI controller, which will generate the reference for voltage. For Q axis voltage, here the D axis voltage. Again we convert the DQ into the ABC quantities so that we can generate the PWM signals for the grid side converter. Is it okay?
Yes, it's now okay.
For others also, Harsh and Rahul, Sunil, is it okay?
Yes, sir.
Okay.
Yeah, okay, it's okay.
Okay, so let us then move to the next portion. So if you have doubt in this DQ and frame, you can study when there is a good book on this. You can refer that book. I'm not remembering the name of the book. The author is Yazdani. So it's a very good book. Why do we need this DQ frame? And why PI controller is not enough, is not suitable for sinusoidal quantities? Then we have to go to PR. Then how to design these controllers? From where we are getting this IQ star, why it is depending upon these quantities? Everything we can, depending upon the differential equation that we have, we can convert them into DQ frame from ABC domain. So that you can refer for more clarity. So the next topic that we discussed was the battery management system. This also we have discussed in the lecture, the week 3. So just let us quickly review. So we are using this battery management system as several functions. So first of all, we can monitor this voltage, current and temperature of each cell. Then we can also do online estimation of these SOC and SOH, which is very important for every battery pack. Because we want to know how much power and energy capacity is still left inside in the battery and how much we can perform with the remaining capacity. Then one major function is this cell or module balancing, and that can be of two types, active and passive. So in this demonstration we saw one active and one passive technique, demonstration of these two techniques. So these are the different causes for cell imbalance. So first we saw this passive balancing. We use this, there are existing ICs for passive balancing, so we can use them. And so this is the passive balancer IC. They also provide protection against these different short circuit, overload, overcharge and over discharge. So because of that only, once a cell reaches its limit, one of the cell reaches its limit. So this is during the charging mode and this is during the discharging mode. So DC power supply can be used to charge the battery, and rheostat which will act as a load for discharging. So during charging, if one of the cell, so here we are using 3 cells. So if one of the cell reaches the limit, then the MOSFET which is inside these IC, there are 4 MOSFETs. So MOSFET 1 and 2 are activated, and as a result of which the charges other are also charged to the same level. So once all the cell reaches the same voltage, which is the upper limit, that this is the threshold voltage, so the protection IC which is inside this, it activates and it stops the charging. So here we are equalizing the voltage on all the 3 cells. Similarly, in the discharging also we are doing the same thing. So if one is discharged, then the MOSFET will discharge the others also, and all the reaches same level, then the IC will be activated and the discharging will be stopped to protect against the over discharge. So then we discuss this active balancing using CHIL. So this is also a very important thing which you can, if you want to do work in future, you can see how we are using this Opalati here and the DSP processor to do the simultaneous real-time operation. So what we are doing here in Opalati, this is also a processor, this is also a processor. So this is a DSP based processor. This is also a processor. So in OpenRT we are making this system. So it is explained here in this figure. So this inside OpenRT, since we are considering 3 module battery pack. So here it is saying n, we can have any number, but in demonstration we have used 3 battery packs, and each of them has this buck boost converter. And then these switches, they are driven by this driving circuit. So inside OpenRT we have this entire system, and we can get some output from the OpenRT. So OpenRT, we can see here this green, right? This green. So one is input and one is output. So from here we can take, so this is analog output. So we are taking 7 outputs. So we are taking 3 currents, these currents I1, I2 and I3, 3 currents, and then we are also taking SOC. So SOC level for all the 3. So 3 SOCs and one the demand mat, which is this PD. So these are the 7 signal which we are taking out from the OpenRT. So these are all analog signals, and this is a DSP based signal, digital processor signal. So it will do every computation in digital domain. Since these signals are in analog domain, so these DSP will be having ADCs which will convert these analog signal into digital domain, and then the DSP based processor can do processing on that. And this is the PC which can be used to program this DSP based processor. What type of processing we want to do, we can program it inside this host PC. So these processor also come with some softwares. They have control suites which we can install and write codes. So since we are getting 7 these signals and we want to generate these pulses, firing pulses for these driving circuits, so that we can manipulate these switches in order to do the cell balancing. So we want to ensure that the power is shared among them such that the cells are balanced. So this processor will do something. So it will compare these signals with the reference signals, and then they will generate these firing pulses. Here in DSP based signal we have these EPWM pins which are used to generate the firing pulses. And also inside this we have one controller. So we have one PI control which is used to control these voltages. So we want this DC bus voltage to be fixed, to be regulated. So that is also done using this controller. So then after generating the firing pulses, we send these digital signals again into the OpenRT, because this system is inside the OpenRT. It is inside OpenRT. So one way is to make the system on an IC, and instead of IC, OpenRT use that actual physical hardware IC. But we don't have that, so we are using OpenRT to mimic that IC. So the OpenRT will behave similar to that IC because it is doing computation at microsecond level. So it is as if everything is happening in real time, very quick, very fast. So to and fro this will be happening. It will be sending these signals and it will be generating pulses. So this will be happening at a very fast rate. So whenever we make some changes, the changes will be reflected very fast. Is this clear? So here also you can see these are the ADCs which are and we are giving 3 currents, 1 PD and 3 SOCs, and then it is generating the PWM signals. So all these processors, they have operating range, voltage range limit. So here this is having a voltage limit of operating voltage of maximum 3.3 volts. So whatever signal which we are giving from UPLRT to this DSP has to be less than 3.3 volts. So we scale our output to 3 volts to leave some threshold, room 0.3 volts to be on a safer side. So we scale them to 3 volts and then we provide it to the processor. And the output we can see here also on this DSO. So is it clear, Jay? Harsh? Okay, then let us move to the next one. So this is our EV part. So can anyone of you tell me why do we need this DC fast charger? So let us first discuss the 3 modes, then I will come to that question. So we have 4 modes. One is the mode 1. So this is the first mode 1 where we can directly connect it to our socket which are available in our homes. So we don't have any extra safety layer in between the socket and the EV. So generally we do it at home, directly plugging it into our sockets. Then second is mode 2. We can see nowadays the EVs which we have. If you have one at home, you can relate it to. So with EV they provide a portable charger that we connect to our socket. So this pilot or control blocks is same as this. Then we are connecting it to our socket available at our home. So these are the portable charger which we can charge, with which we can charge at home and in public charging stations outside also. Then we have this mode 3 which are directly connected to the network, to the grid. So they are wall mounted. They are nowadays available in shopping complex, the parking lots of shopping complexes. You can find these type of chargers. So all these chargers are AC. Here we can see. So in between, because EV charging, in EV we have a battery and it is charged with DC. It operates in DC. So if we are giving AC, then in between we have to convert the AC into DC. And for that we need one onboard charger. So this is that onboard charger. So it is a AC-DC converter. Then we have this mode 4 where we don't need this conversion stage AC to DC. We can have in between we can have one DC-DC converter and then directly charge the battery with the DC. So here we can have up to more than even 200 kilowatts. The benefit of these fast charger is that we can charge our battery very fast. So these will be the public fast DC chargers which will be available in near future. So we will be able to charge our batteries within 10 to 15 minutes. So now can you tell me why can't we have this DC fast charger inside the car itself?
It will be very bulky, na? If you put fast charger on the vehicle, weight is the main concern.
Size will increase, weight will increase, and most importantly, the cost will increase.
Yeah.
So we don't want that. So we'll just as we have these petrol pumps, we can have these charging stations, and we can charge within few minutes. So
Mode 1, mode 2, mode 3, we cannot say they are charger. They are just like adapter, just like plug points, we can say. Actual charger are inside the vehicle. You can see they are not actually charger. They are just the power points.
So these are points only. This is these modes are the different modes of charging. So
the mode of charging, but actually, in the common sense, people tell like charger, like actually they are not the chargers.
Correct. Actual onboard charger is inside the vehicle.
Yes.
But this mode 3 provides several functionalities that it can communicate, it can help in automatic charging, and several features are there which this mode 3 can provide, even mode 4. So these two can provide several facilities like vehicle to grid, P2G.
Yes.
So they have communication facilities available.
Yeah. Okay.
Yeah, so then we have this which I was talking about. This, so we call it EVSC. This can also be called as EVSC, electric vehicle. So EV supply equipment. So it will connect the charger to main supply and offer these different types of functionalities. And then we have this cloud which will interact with both this EVSC and this user through the mobile application, and we can do several functions. So now let us know this. This was not explained much in the lecture, so I will just go through them. Do you know what is the difference between these four type of thing? Actually, there are different types of charging methodologies, and the most simple one is the basic, just on and off charging. Connect the charger to the grid and then disconnect. So simply, just as we plug in and then we take it out. This is a simple manual, we can say. The next step we can say is this one, which is the time of use tariff pricing without automated control. So what we are doing, we are, just as we saw in the demand side management, we will give some price signal to the customer and the consumer, depending upon the price. When it is cheaper to charge, they will charge the EV. When it is costlier to charge, they will not charge. So we are trying to shift the demand. That is why we are using here TOE, time of use tariff, and it is not automated. So it will depend upon the user. User can choose to charge or not charge. Then we have this dynamic pricing with automated control. So here, time of use pricing, generally we have two prices, one for peak and one for off-peak hours. In dynamic pricing, we can have different prices, several levels of prices, even within peak and off-peak. So more than 2 levels of prices we can have. And this can also be automatic. So based upon user may enter into a contract and there can be automation. The aggregator, EV aggregators are there. They can control the vehicle of the customer if the customer is willing. So he may have certain rules that my SOC should not go below 50% whenever I come to take my vehicle. So all the different things can be there in the contract. Then the one is this bidirectional control, where we can have different options. Suppose there is one research going on that if there are two vehicles going side on the road, highway, and one vehicle, because everything are, so for this we will need communication also. So what will happen, suppose this vehicle 1 is having the SOC is near, it is about to deplete. So it is about to be discharged fully. So he wants to charge the vehicle, but the charging station is not nearby. But he knows that nearby there is one vehicle 2, which has a SOC sufficient so that he can charge and reach the charging station. So these two vehicles can communicate with each other and transfer the charge by, we call it contactless. So this can happen by contactless charging. So this is vehicle to vehicle, which is also, this is not mentioned here, I was saying. So this is also one option, you can also add here, vehicle to vehicle also, V2V. So then vehicle to grid is, suppose you already have your batteries, EV is fully charged and grid wants some power. This will especially happen when during the peak load. One single EV may not be able to provide that much huge amount of power, so generally these functions are performed by an EV aggregator. So EV aggregator will pool some of the vehicles in a parking lot, maybe inside a parking lot, inside a building, or inside a colony, in a locality. It can aggregate, and then during the peak time these vehicles can push power into the grid so that the peak load can be supplied. Another option is home. Suppose especially we have UPS for backup power, emergency power. Similarly, these vehicles can also provide that backup power. When the power from the grid is not available, we can use the power which is available inside our vehicle to do some minimal works, to carry out those essential tasks. Similarly, for building also we can do that for building. So here the vehicles which are available in the parking of the building, they can supply the power to the building in case of emergency. So is this clear?
One question.
Yes.
How would it be possible V2V vehicle with contactless charging?
Yeah, it is still in research, but it is possible. For that they have to, since they have communication facilities available, so they have to be in a very close proximity. The main drawback of the contactless charging right now is that
Losses.
Losses, because of the contact, which is right now you would have, we use these contactless chargers. Nowadays we have mobiles are also being charged, but for that we need to have the contact should be the gap between the two, the transceiver and receiver, between the two coils, inductive coils, should be very less. That is the biggest challenge. So right now the phones that we charge, we place it on that instrument only, or very near to that, then only it is able to charge. Otherwise it is not able to charge. So main problem with this is the gap between the two vehicles. So that has also the alignment is a problem sometimes. There are some chargers, even public chargers. This is a pilot project in some countries. They have a charger which they have a contactless. So they have a plate in the charger and one plate is there in the vehicle. These are the inductive plates. So when these two plates will align and the contact is less, so they will charge. But if the alignment is not proper, then also the charging is not proper. So these there are some issues with this. So here also at IIT Bombay, some of one student is working in this contactless charging. So we have to work a lot in this direction to achieve this, but it is possible. There are some highways even in China. They have made one solar highway, so the vehicles can dynamically they can ride on that highway slowly, so that they can charge dynamically. They are experimenting with that, so it is possible.
And is it possible to vehicle with contact charging through cable?
Contact is also possible.
Through cable.
Contact is possible. This we do for airplane refueling. We use this. Even for spaceship, for ISS, we use this type of thing. We align them together and we use this. In case of airplane, we use that cable or pipe for refueling. Similarly, we can do that for vehicle also. But for that also we have to, communication will be required. We have to maintain the speed. If it is autonomous, drivers are there, they can do that. Also V2 we can also help in several other things like maintaining optimal distance between the two vehicles so that there is no collision. There are several things which can be done using this vehicle to vehicle communication.
Thank you.
So any other question? So then let us move. So this is the final topic, so lecture 5. So here we discuss, because half of these things are already discussed, so we will not go much into detail. We will directly take questions. So here we discuss this different components in hybrid AC-DC microgrid, the structure of hybrid microgrids, then what is the need of storage, then management of microgrids. So there are two management. One is power management, one is energy management. So in power management is used to affect changes which are happening very instantaneously, very quickly. So these are the high frequency changes. So for example, the voltage and frequency regulation that we do, so we do it very quickly for very short term basis, so that the control loop has to act very quickly in these cases. Then for energy, we have energy management. We want to have overall power, the load and generation balance, to achieve some certain desired outcomes, such as we want to minimize the cost. So we want to do it optimally. So we want the system to work with optimal cost. There may be other objectives also, like we want to minimize the losses in distribution system. We want to minimize the emissions. We want to increase the life of the assets. So all these things can be the objective. So this will be ensured by this energy management. Then we have classification of control. This also we have seen in the previous weeks. So we have 3 type of control possibles. Do you recall what type of controls are possible? So I will give you a hint. One is centralized. Can you tell me the other 2 controls? Harsh, can you recall?
Local, decentralized.
Yeah, one is correct. Good. So one is decentralized and third one?
Local.
No, so local and decentralized are same.
Okay.
So we are in decentralized, we are locally controlling. So each of the DG will be controlling itself. So that is local or decentralized control.
Okay.
And in the centralized, one centralized controller is there which is controlling all the DGs. And if the link of one of the DGs break, if there is a loss of one link, then there will be a problem. So that is a drawback of centralized system. Although we are able to achieve the global objective, but by losing even one link, there will be a problem in achieving that global optimal. In decentralized, the problem is we have no information about the global objective because everyone is just doing its local control without any idea about what is the global objective to be met. So, which one is the third one then? One is centralized, decentralized is over. So, both are having some disadvantages. So, we went for the third one. So, what do we want?
Sir, distributed method.
Correct. Distributed is correct. So, what do we want? We want local control also. Because the problem with centralized is that if we lose one link, then the objective is not achieved. So we want local control also, but we want to improve this reliability of the centralized system also. So that even if one of the link goes out, we can still achieve the objective with a good accuracy. So this is the centralized. So in decentralized, we are each of these DG will be communicating with its neighbor. So this is we also call it peer-to-peer communication. So here if one of the links also goes away, then still we can do something. So this is the distributed control. So we are trying to harness the advantages of both centralized and decentralized in this distributed control. So then sorry for this, I have to remove this. Now let us move to questions. So whatever we have discussed till now, we'll be doing questions on that. So hopefully we'll be able to recall something. So I think this was not discussed. We can discuss this based upon what you have heard in lecture. You can try to recall this. So what is the purpose of the bleeder resistance connected across the snubber capacitor? So do you remember this? So this is with respect to the solar power generation demonstration where we were using. So for each IGBT module we have two IGBTs and each of them have one body diode. Then across each module we have one snubber capacitor. Snubber capacitor. Then for DC, then we have DC link. And for DC link we use this bleeder resistor across this capacitor. So why do we use this? So here we have DC link.
Option A.
Option A. That is correct. To discharge the stored energy in capacitor when the inverter is not in operation. Because if we do not use this, then that stored energy can flow into these devices, and these devices can be damaged. Is it okay? So B option is not correct because the resistor cannot store any energy. It only dissipates. So energy storage element are L and C. So B is right out. It is outrightly rejected. Okay, now this is the question for snubber capacitor. So why do we use the snubber capacitor?
Option B.
Correct. So why and how snubber capacitor is able to protect the switches? So we have this snubber capacitor here. So if you see the impedance of a capacitor is 1 by omega c, correct? So whenever there is a voltage across this capacitor which is fluctuating at a very high frequency, then this omega will become very large and this will become 0. So this capacitance offer a very low resistance path as if it is a short circuit. So all the high frequency voltage signals will pass through the capacitor and protecting this IGBT module. Is it okay? Okay, so let us move to the next question. So this is the next question. Which of the following control loops are there in the grid connected PV generation? So we saw both single stage and dual stage conversion systems. So in both of them there were common loops, control loops. So one was MPPT loop, then we were having the DC link voltage control. Then we are having the current control loop, which is the innermost loop and the slowest loop. Then we were having this, we are feeding this to the grid, and we are having one PLL here to generate this theta. This theta is actually used for the DQ frame transformation. And this, so PLL synchronizes this theta of grid, which is the angle at PCC, and it generates same theta here. So it locks with the grid angle, the voltage angle of the grid. And we are getting the same theta, and as a result of which we are using this, we are able to generate this DQ frame signals. So what are the correct options here? So we are having MPPT here, and the voltage, DC voltage control, current control, and PLL. So Jay, are you there?
Option D, all of three.
Yes, correct. Now this is a good question. So I think this is a very important principle to note, to remember. So we have to correct select the correct option with respect to the DC link capacitor. So here we are having the DC link capacitor, and then we have this DC-AC inverter, then we are giving it to the grid. So grid voltage is VG and the DC link capacitor is voltage, let's say it is VDC. This is the peak voltage.
Option C.
Should be rated more than the peak grid voltage. That is correct, but why it should be more than the grid voltage, peak voltage?
Because the power transfers from DC to grid.
Yes, we want the power to be transferred from DC to grid. So for that we need to have voltage difference, correct? Yes. So we need to have sufficient voltage difference in order to ensure that the power transfers from the PV panel to the grid. If this difference is less, then we will not be able to transfer sufficient amount of power. Then the next question is, identify the correct statement with respect to the solar inverter. So option 1 is it converts variable AC power from PV panel into fixed AC. It operates only in DC in the grid connected mode, and it cannot provide grid support services. So is option A correct? I think option A is very easy. It is saying variable AC to fixed AC. Here we are having a solar PV. So what do you think? Is option A correct?
It's not correct.
Yes. Why?
Generate PV panel gives DC power only. No?
Correct.
Output is DC.
So we need here it's DC, it converted into AC. So this is wrong. What about option 2? B.
It's also wrong.
So why?
Can operate only in grid connected mode.
So it
Standalone mode also it can work. No? It's not.
it can operate in standalone mode also, or the islanded mode. And what about C? Option C?
Cannot provide grid support services. It provides.
Yes.
Grid support
It
services
provides. It can provide reactive power also.
Yes. Provides.
Depending upon we can change the reference, Q axis reference.
Yeah.
Then we can provide the reactive power also.
Yeah.
So that is so. So all the options are incorrect.
Yes.
Good. So let us move. So 3 major factors to be determined for performing active cell balancing. So what are those 3? Mode of charge distribution, converter topology, balancing strategy, or all of the above? So what will be the correct option for this? This mode of charge distribution means how we are distributing it in the balancing the charge. Is it cell to cell, cell to module, for power sharing. Then this is converter topology. So what we saw in that that slide, here we were modeling that system of 3 batteries inside the Opal RT, and each was having one buck boost bidirectional buck boost converter. So here we are using buck boost converter, so we can, that is the one of the kind of topology. There can be other topologies also which can be used for cell balancing. So that is the converter topology. And then what is the balancing strategy? So which parameter, control parameter are we using to ensure the cell balancing? So which parameter were we using for cell balancing, which was demonstrated in the lectures? Do you recall? We saw this picture, right? So we were giving 7 inputs to the processor, and then we were receiving outputs for these 3 converter. These were the duty cycles. So what were these 7 inputs to the processor, DSP processor?
3 currents and 3 SOC.
Correct. So we are using 3 currents and 3 SOC. So in that, these are the 3 factors which determine, which need to be decided for performing the cell balancing. So we need to know. So here we are using the SOC strategy. We can also use voltage or SOH. So here we are using SOC. For converter topology, we were using this bidirectional buck boost converter, and the mode of charge distribution was here power sharing. So these can change depending upon the different cell balancing technique used. So all of them. Yes. So what is the full form of CHIL? This is the easy question. Anyone? Is hill climbing?
No, first one.
Yes, I have introduced this option hill climbing because I remembered one thing. So for this MPPT, that we have MPPT algorithm, right, for solar and wind. So for solar we have different types of algorithms for tracking the maximum power point. One is that perturb and observe. So we will introduce some disturbance and then we will observe voltage and current, and then depending upon the change in the voltage and current we will see on which side are we. So this is our PV characteristics, right? So suppose I am here, I was here, and if I make a change in this direction, so here voltage is V1, V2. If I go into this direction, then delta V is positive here. And dp by dv we can say it is also positive, so slope is positive here. So we can again add the disturbance. So we know that we are on this side. If we are on this side, V1 and V2 here, and if I add I add voltage, some delta V will be here, V2 minus V1, which is negative, and the dp by dv is also negative here. So we know we are on this side, and by adding voltage we are going further away from this maximum point. So if we are on this side, we know that we have to reduce that change. So we can again go to this point. So again and again we add this disturbance and check on which side of the curve are we. And this is done by changing the duty cycle of the converter. So we change the duty cycle of the converter in steps. 0.01, and we will check where the solar PV is operating on which side of the slope of the curve, and then we can reach to that point. So that is one P and O. Then one is incremental conductance. And there are other different types of. So these two are called this hill climbing methods, because we are climbing hill here, from this side also and from this side. So this is a kind of hill, so these are called hill climbing techniques. So from there I remembered this and I added this option here. First one is correct. Now let us move to the next one. So which of the following is correct with respect to DC fast charger? So it is onboard EV. Is it correct?
No, not correct.
Yes, so this is wrong. And then it requires thin cable to allow high charging current without cooling requirement.
No, it's also wrong.
Why is it wrong?
It should need heavy cable.
Yeah,
Right.
because we are saying it is around 200 kilowatts, so current will be very high, charging currents, and for that we need high cross section. And even if we want to use a smaller or thinner cable, then we have to have proper cooling arrangement. Then what about the option 3? Fast charging operation is done in the constant voltage mode.
Should be correct.
It should be constant current mode. One of the problems with fast charging is that it quickly reaches this level. So if it quickly reaches here, so problem is that it is not able to charge fully. So we have to, for initial part, for fast charging, the mode should be constant current, and after that, once it reaches to a good SOC level, we can shift to the constant voltage mode. Because as the SOC and voltage are linked, when the SOC, suppose when the battery is fully charged, maybe say 4.2 volt, just as we took in that example, 4.2 and 2.4 volts. So this is when the battery is fully charged, and this was when the battery is fully discharged. So this is for 100% SOC, and this is for maybe, let's say, 20% only. So voltage is dependent upon the SOC. If the SOC is less, voltage will be less. So initially, if we are in the constant voltage mode, then how we will not be able to increase the SOC much. So initially we have to be in, the battery has to be in the constant current mode so that we can build the voltage. And then once it reaches to a good SOC level, we can shift to the constant voltage mode. Is it okay?
Yes, okay.
Yeah, so this should be constant current, so none of the above. All the options are incorrect in this case. So this is the DC fast charger. So this part is outside the vehicle, and here is the vehicle. So this is the supply which is given to fast charger. Then we have a rectifier for DC to AC. Then for that whether we want to operate in CC or CV, constant current or constant voltage mode, that we have to change. So here you can see it, constant current and controlled voltage and controlled current. So this is able to supply that. That is why we are having this DC-DC converter stage here, so that we can supply a variable DC supply. Based upon our requirement, we can change it.
So how can you define that change from CC to CV? Means as my understanding, before the slide, you were telling that from 20% to 100% constant current.
No,
but what
it's not from 20 to 100 it will be constant. Between up to certain SOC it will be constant. After that, because what happens when the voltage will drop very less when the SOC is high. So as the SOC declines, the voltage drop will also increase. So near the full charge capacity, so maybe between I don't exactly remember, but between 80 to 100, the voltage drop will be much less. So we can safely operate in that constant voltage mode. So based upon SOC also we can decide that. Because we have this inside these converter, we can have these SOC voltage characteristics. We can store it in the form of a lookup table. So based upon the voltage, we are always monitoring the voltage in SOC. So we know at this voltage what will be the SOC. And also we have these other methods for estimating the SOC. This is one of the methods. So based upon these estimation, we can take decision whether we want when do we want to switch from CC to CV.
Okay.
So then we have these safety interlocks also. So these are also important. So these are inside that these charger. We have different types of charger configurations. Combined CCS is there, CHAdeMO is there. So CHAdeMO is Charge Day Move. It's a European standard. So these safety interlocks are helpful in de-energizing the EV connector, and also it can help in stopping the charging process when there is a fault or there is improper connection between the charger and the vehicle. Then this BMS is there, so it will be communicating with this charger, so that because it is monitoring the status, SOC, voltage, current, everything, we need to provide this so that it can provide this variable supply. So there will be this communication. So when the charger pins that we have, different type of, so they have different slots like this. So some of these are dedicated for the communication. So they will be having, and they ensure the communication between the BMS of the vehicle and the charger. Yes. So there is a communication between charging station to monitor the V and I and operate the protection circuit also. So these are some of the problem with the fast chargers, some issues with the fast chargers. So one which we have also discussed in question, that we require high, the thickness of the cable has to be much higher because of the large amount of current, charging current. And if you want to have a thinner conductor, then we have to have proper cooling requirement. And because of higher current, there are high losses in the charger as well as in the electric vehicle. So because of the losses, there will be degradation in the capacity. Also, there is a curve between the this is number of cycles and the this is the number of cycle, and this is C rate. So as we increase the C rate, the life of the battery reduces. This is also true with the depth of discharge also. The more the depth of discharge, the life of cycle reduces. Life cycle of the EV will reduce, battery. So higher the C rate, there will be reduction in the battery life. So that also, and in the fast chargers, the C rate will be high. So for that, we need to have those battery technologies which can support very high C rates. There are some, like LTO is one such technology, battery chemistry, which can provide up to, I think, 6C to 10C. 6 to 10C of C rate is possible. But the batteries that we use right now, they don't, LFP, it doesn't provide up to 6C of C rate. So that is also a problem with fast chargers. So we have to change the battery chemistry for that. Then when fast charging, this is another problem. Then if fast charging, the SOC may not reach to up to 100% because of lag between voltage and SOC. Then this we have discussed. So okay. So next question is, which of the following is or are advantage of smart charging? So this is true because hosting capacity of the distribution network operator, it will increase. Smart charging will have both vehicle to grid and grid to vehicle. That is why this can help. So increase in system load is not an advantage. We want to always reduce the system load. So the system operator always tries to ensure that the peak load reduces. So this is not a correct option. Then this is a correct option because time of use tariff. If at peak hours the price is high, then they will not charge their vehicle. So in this way we can reduce the peak load also. This can also be done. So in this case A and C will be correct option. And the next is select the correct option with respect to importance of energy storage in microgrid. So can you answer this one? Because we have these
Both A and B.
correct, because we have this solar and wind and they are intermittent in nature. So in standalone mode, if there is no other generator, we only have these renewable generators. Then in order to maintain the generation load balance, we need to have this storage. Then this is also true, the energy storage can smooth the output of the power in the grid connected operation. Then energy storage can be of these two types. One is capacity oriented and the other are access oriented. So capacity oriented, they have slow response. In long term energy balance, they can contribute in that. So we can use them for low frequency power oscillations. So that is why here the ideal storage will be with high energy density and low power density. So that is why we can use battery, compressed air, pumped hydro and hydrogen in this. On the other hand, access oriented, they require fast response and to mitigate the short term disturbances such as the frequency regulation. So frequency regulation services can be provided by this flywheels, supercapacitor or SMES. The superconducting magnetic energy storage. So this is done. Now the next question is so you have to select the possible configuration of hybrid AC-DC microgrid. So now the questions will be on this last topic, like hierarchical control. So which of these is the possible configuration of hybrid AC-DC microgrid? So we can have three configurations. So one is we have AC bus and all the sources and the battery are connected to the AC bus itself. So if it is solar, then we'll be having a DC to AC converter here, and then if it is a wind here. So this will be AC coupled hybrid microgrid. You can have some loads here, and this is our grid. The second option is to have a DC coupled microgrid. So all the sources will be connected to the sources as well as storage will be connected to the DC bus, and then this DC bus will be connected to the grid via the converter, interfacing converter. Then the third option is to have a AC-DC coupled hybrid microgrid. So here we can have sources and storage both on both the sides, and in between we will be having the interlinking converters, bidirectional DC-AC converter, and then there will be a grid. So here all the three options will be correct, A, B and C. So this same is explained here also. Then the next question is, which of the following is not true about the interfacing converters? Interfacing converters can be of two types. One is the interlinking capacitor, bidirectional interlinking capacitor, which are single stage. Then we can have back-to-back converters. These are also bidirectional, but these are dual stage, two stage. Just as we have it in the wind, we have this one rotor side converter and one grid side converter. Here also we have AC, here also we have AC, and in between DC. So AC, DC, AC we can say. While in the interlinking converters, we'll be having DC bus, AC bus, and in between a bidirectional converter from DC to AC. So now can you answer this question? Interlinking converters and back-to-back are two types, so this is correct. Interlinking converters are single stage three-phase inverters, that is also correct. But back-to-back is not single stage, and these are bidirectional, that is also correct. So this is incorrect. This option is not correct. So answer will be option C. Is it okay?
Okay.
Okay. Yeah, so here the main principle is to equalize the DC side per unit voltage with the DC side per unit frequency. So because both are in per unit, so we want to equalize both. While on the back-to-back converter, it ensures constant power mode with respect to both the buses. I think I have missed one. Okay, no, it was incorrect, so this is option C is correct. Then the two categories of microgrid management strategies are, we have discussed this, right? Two management strategies. Yes, in the previous slides we discussed, this is power and energy management. One for power for short term and energy for meeting the overall demand and generation balance. This is for voltage and frequency regulation. This is for optimal operation of the system, ensuring generation is equals to load. This is power and this is energy. Yes, so questions are over. So, is there any doubt in what we have discussed today?
There was a question in the assignment
Yes, which one?
regarding PR converters, PI and PR.
Yes.
Was refers some current. Can you bring that question, the assignment, 9th assignment?
You want me to show that question?
Yeah.
This one, right? Second question.
Yes, integrity identify the. Yes, I have selected for both for synchronous and stationary, A and B both. So
Yes.
whether I was not very sure, but I was.
See, this also, I was talking about this concept.
Yeah.
What is this DQ frame that we use? It is also called as the synchronous reference frame.
Okay.
So, what is the problem with this PR is, so why are we using PI? Because we want the simple control. PI is very simple. But the problem with PI is that it cannot operate with sinusoidal signals. If it will operate with sinusoidal signal, there will be error. In this, there will be steady state error.
Okay.
So that is the problem with PI. So to solve that problem, to resolve that problem, we want to operate with sinusoidal also, and we want to use PI also, but we want to do some modification so that the error can be reduced and we can track the signal very well. So for that, the PI is converted into this PR. So PR, what will happen, we in front of that PI we will add some lead lag compensators.
Okay.
So that we can track the output. But introducing these compensator will increase the system order, and that
Yes.
yes.
Correct.
And the design of the controller also becomes little tedious. So some people have done that. PR is also used. So with sinusoidal signal we can directly use PR. That is also possible. But if we want to use PI only, then we have to convert those ABC signal into DQ frame. So this synchronous reference frame here means the DQ frame.
Okay.
And this C is not correct with the depending. So we cannot use PI, PR irrespective of the reference frame.
That's it.
So this there is one book we can refer that. I will add the link of the
Yeah.
author and
Yes.
name of the book in the references. You can refer that. That is a good book for this voltage source converter design. I think name is same, voltage source converter design, something like that. Amir Yazdani. Author name is Amir Yazdani. So that you can
Okay.
refer. So
Which
this
publication? Indian publication,
that
sir?
I have to check. Let me check. Just a
Okay.
minute. It is Wiley publication.
Okay. Well, okay.
Voltage source converters in power systems, modeling, control and application.
Okay.
So I will write it here in presentation also so that you can check. While seeing the video also you can check.
I'll just add the link. That will be better. Okay.
So I will share the reference.
Yeah. The reference. Yeah.
At the end of these slides.
Yeah.
Okay then. Is there any other doubt?
No, it's clear. Quite clear now.
In the same assignment, 10th question.
10th question, just yes, question 10th.
I have selected in a microgrid we cannot use two storage elements such as lead acid battery and supercapacitor together. Why you cannot use?
Even what about this? Is this option also correct or incorrect?
Yeah, actually, response time of the supercapacitor is fast.
Yes.
It was clearly mentioned earlier in slides.
Yes, it is fast.
But here it is given as wrong answer.
Yes. So this option should also be correct B, right?
See, the question is identify the incorrect statement.
Yeah.
So in a microgrid, we cannot use the two storage elements. That is incorrect. We can use, right?
Yes. think instead of lead acid they wanted lithium battery, I think. Because problem with lead acid is that lifetime of lead acid battery is less in comparison to the lithium ion batteries. So in
But this is also
microgrid
correct.
we prefer lithium ion batteries.
Yeah, it's okay. But this is also correct statement. No? Response time of supercapacitors is fast compared to lithium-ion batteries.
This is correct.
Then how could it be possible? Incorrect answer. Incorrect statement.
So this is a correct statement, no? Response time is fast. So
Yeah,
this
yeah,
is
correct
not
statement.
So we have to select incorrect. So this is correct. This is also correct. So C, you are saying C is also correct.
C is the answer because I have seen some photo also. There is a microgrid storage elements, lead acid with supercapacitor. In earlier slides.
So based upon the options, if we see, then only this option seems to be incorrect. Others are correct.
Yeah.
So that is why this is the option. Relative with respect to other options, if we see. Otherwise, this is also correct.
No, it was correct. Response time of supercapacitor is fast.
Yeah, so we have to. This is correct, no? But we have to identify the incorrect statement.
Yeah.
So.
But answer is given incorrect statement is response time of supercapacitor is fast.
Oh, sorry. Yes.
It is the C. I have selected C, but I wonder.
Okay, sorry. I am also confused. So, yes, I think we'll correct this. We'll change this.
Okay.
Sorry.
No problem. And one more question. This is not related to today's class or something.
Yes.
Actually, first time I am attending this class.
Yes.
NPTEL courses. I am working professional. Hardly we get time to concentrate on these references, and only I can see and follow the videos.
Yes.
I have applied for examination also.
Okay.
So what is the pattern of exam? Can I get some ideas?
Pattern is same. The pattern which we are following in assignments, same type of pattern is there. MCQs question is MCQ based. Exam is MCQ based. Similar type of questions will be there. So you can prepare based upon the lectures, assignments, and the discussion that we have.
Okay, there is no descriptive.
No, it's MCQ based.
Okay. What is the means? How many questions will be there, and what is the duration?
That even I don't know.
Okay. Where can we get the information?
You can mail the TA for that course TA, or even coordinator. You can mail the coordinator also. Because
everything organized in this videos and but question pattern question papers pattern is not available anywhere.
Yeah, that is not available. Correct. But questions are similar to the assignment and what we have discussed, exactly from what we have discussed. So if you go through these live sessions also, I have summarized all the lectures, so it will be much helpful for you to go through these, and you will get all the summary points inside these videos.
Okay. So it won't be beyond that lectures.
Yes, no. It will be from everything will be from lectures.
Yeah, in videos there are so many references, and you are also mentioning references.
Yes, that is for additional information. If you want to, actually, this course is a PG level course, and it is more oriented towards those who want to pursue career in research field. So if they want to further go into detail of these topics, they can refer those references.
Okay, thank you.
So do you have any feedback for the live sessions? Is it the way we are proceeding for the live session, is it okay, or you want some changes to be made?
Yeah, it is very good. Hardly I have attended 3 classes maybe due to my busy schedule. But maximum I am getting knowledge from this live session.
that is very
And it is like interactive and question and answers and discussions.
good.
It is more interactive type.
Yeah, that
It is
was the main objective of these live sessions, because the recorded video lecture we are not able to interact. So here we can ask doubt questions live. We can interact with each other, and also we can briefly overview what we have studied in the lectures.
And your way of presentation is also direct point to point. There is no roaming around the subject. It is quite impressive.
Thank you, sir. The compliment. So I think if there is no doubt, then we can end the session then.
Yeah, it's okay.
Yeah, so thank you for joining today, and so hope to see you again next week, same time.
Yeah, thank you. It's a very good session. Thank you.